we have talked about tidal and subtidal variability. To estuaries, we saw how tidal variability modifies this framework of the two-layer circulation in estuaries, how the tides can induce tidal straining, and also in the long term, it can modify the bottom stresses and it can produce tidal stresses that act with the barotropic pressure gradient. We saw how the wind can modify the estuarine circulation. When it blows seaward, it can enhance the estuarine circulation, and when it blows landward, it acts against it. And also we mentioned that if the wind has the right period, it can produce some seiching in the basin. And we also saw that how atmospheric forcing can affect sea level and in turn the estuarine circulation by pushing water in or drawing water out of the estuary. And we saw how the effect of the atmospheric pressure can be parameterized through the inverse barometer, which is 1 centimeter per millibar change in sea level. Okay, so today we'll continue talking about how this estuarine circulation is modified. And first, by looking at how the tides modify the estuarine circulation in the long term. So let me ask you a question. What do you think will happen to this estuarine circulation when the tides are strong during spring tides versus when the tides are weak during neap tides? What do you think will happen to this estuarine circulation? Will the estuarine circulation increase during spring tides? When the tidal currents are stronger, will the estuarine circulation increase?
Yes.
Yes.
Yes? What if I tell you no?
Let's say cheating.
Or you'll say I'm crazy, right? That's right, because it sounds counterintuitive, but that's what tends to happen regularly. In many cases, I shouldn't say regularly. In many cases, that's what happens. What happens is during spring tides, you have enhanced mixing, increased mixing relative to neap tides. So what does mixing do to the estuarine circulation? It hampers it, right? Because the density gradients get weaker, so the estuarine circulation gets decreases. In contrast, during neap tides, there are weaker mixing, so the density gradients are allowed to adjust. Remember the example we saw about the response of the Chesapeake Bay to Hurricane Felix, that we had enhanced stratification because it was after neap tides. Anyway, we'll look at some examples about this. So first, I'm showing you this figure of the tidal amplitude in Panama City for this year throughout the entire year. What we're seeing there is the envelope of the tide. So if you can think of the tides going up and down very rapidly, and this red line being the envelope of those oscillations. So it tells us how large those variations were. So this tells us when spring and neap tides occur throughout the year, and you can see that sometimes the spring tides are larger than other times. For example, the largest spring tides of the year we should expect in June in Panama City, and the weakest will be in March. So the range is not that as high as it will be in June. That's what this shows us. And also, the neap tides will have a very small range in March also, but also in September and October. But the lowest range, the smallest range in tides, in the neap tides, will be in March. And if you go and look at the website that I recommended that talks about tides, you'll find out why. This is because of the tropical tides and the equatorial tides, and where the moon is in the orbit and the earth is in the orbit around the sun. So that's what determines the annual variations, right? So, but the main reason of why I'm showing this figure is to note here the spring to neap variations. So within 1 month we have 2 neaps. Say in January we had 2 neaps, which are these ones, and 2 springs, which are this one and that one. You see that? This month in February we have this one is spring, and this one is spring. and then this one is NIP and this one is NIP. So we're going to be close, for those of you who are going to the field trip in Panama City, we're going to be close to this spring tide. Right. And again, the main reason why I showed this is because if we wanted to sample spring tides in February, we don't want to sample these spring tides because there are these other spring tides that are larger. So you can see that consecutive spring tides differ even within 1 month. So you have to be aware of that. Same with neap tide. So if you want to sample either spring or neap tides, you have to look at this type of representation, because you're not sure you don't know whether you're sampling the spring tides. For example, these spring tides in May are sort of wimpy as compared to these spring tides in May, right? So you have to be aware of that. So that's in Panama City. In Ponce de Leon Inlet, that's the situation, and we're going to be sampling right also around here. And notice now I show the phases of the moon here. N, what do you think N means? New moon, and F represents full moon. So notice here at the beginning of the year, the largest spring tide occurred during the full moon. Then during February, the two spring tides are sort of similar, but then by March, the high spring tides are during the new moon, not the full moon anymore. So this switches again throughout the year. If you see here, by October, we have that the high spring tides appear again during the full moon. So between March and August, we have the high spring tides during the new moon. So also, if you go by the moon, it won't tell you all the time which one is highest or which one is lower. Right? So that's something to take into account too. That not always the new moon is the largest spring tide of the month. It can be the full moon, or vice versa. Depends on the month and the year. So that's something to take into account when you go and sampling. So you can see here that this tremendous variation throughout the year will cause also different stratification conditions throughout the year, as you may imagine. How so? Well, let me give you an example here. This is an example from Long Island Sound. This is Long Island Sound. This is Long Island. New York City is right here, Manhattan. And this is Connecticut and Rhode Island, Massachusetts. Here seen in a different perspective. Here's Long Island. So the data that I'm showing you are time series right around here where the arrow is. You see where the arrow is? So toward the eastern end of the estuary. So what we have here is records time series of temperature, salinity, density, and velocity during almost 1 month. And we have values at different depths, 15.5 meters and 27.5 and 27 meters. So the orange line is could represent the upper layer of the estuary, and the blue line could represent the lower layer of the estuary. Now, what have we done to this data? Why are they so smooth? Why are these time series so smooth? Why don't we see the tidal wiggles? We have filtered the tides from this data. Okay, so in reality, you should see all the tidal oscillations in these lines, but we have filtered them out. So what we have here is non-tidal variations. So one peculiarity of this, of all these time series, is that you see here the temperature is stratified in this period. Also is the salinity and the density, and then it gets destratified. And then it gets stratified again. Right. So which of these periods, this one, or that one, do you think is spring tides? Right, the middle. So right where the arrow is, we have spring tides. And also look at the flow, the mean flow. Look at the flow near the surface, which are the arrows. These arrows going in that direction means that they're going toward the west, that is into the sound. So negative blue, they're not arrows, they're sticks. The negative sticks means that the flow is going toward the west into the south. So notice that during this period of higher stratification, we have stronger net flows right here and right here, stronger inflows. And during spring tides, the estuarine circulation really gets decreased right there. Right, so we see clearly here the fortnightly variation that I explained, that I was talking about before. During spring tides, the tidally induced vertical mixing increases. That smooths out the gradients in the estuary, and the estuarine circulation gets hampered. Whereas during neap tides, there's the tidally induced vertical mixing gets reduced, and then the horizontal density gradients are allowed to adjust under gravity, and the estuarine circulation is stronger during neap tides. Okay? There are many examples in the literature that show this type of behavior. There are others that don't show it. So this is not universal. I just want you to understand that. In some systems you see it, but in some others don't, because the geometry will have something to do with that variation. And that's something that we're still trying to understand. Why is it that you see this in some systems, and why in others you don't? Okay? So one way to look at the same fortnightly variation is by looking at the competition between what and what. What are we looking at here? Yeah, the competition between the stabilizing energy from stratification, the buoyancy here, compared to the destabilizing energy from vertical shears. Right? So this tends to stabilize the water column, to stratify it, and this tends to mix it. So it's called the overall Richardson number. So we have observations there at two different depths. We can calculate the vertical gradient, this delta rho dz. And we also have flow u and v at different depths. We can calculate these two. So with that, this is also the low pass filtered behavior of the overall Richardson number for that period that I showed before. And the critical value, what's the critical value that tells us whether mixing will begin or not? Yeah, 0.25, 1/4. So that's a theoretical result from lab experiments. It doesn't necessarily happen in nature, but it's a good reference. So you can see that above that value of 1/4, the overall Richardson, this is the period when the water is stratified. These are neap tides. The water is stratified. The overall Richardson number is at least higher than 1/2. And during the period of spring tides, the Richardson number is lower than 1/4. So that tells us that there's mixing, the stratification of the water column. So that's the period of spring tide. So this doesn't only appear in the longitudinal flow, but also you can see it across an estuary. And we're looking at what is this estuary? I've shown this figure before, that's why I asked you what estuary is this. Sorry? No. That's the James River in Virginia. So if this is the James River, what is this? The Chesapeake Bay, right? Yeah, and I'm sorry to not include a map, a regional map, but so this is a good geography lesson, I guess. Well, not so good, but just a geography lesson. So we have the James River here coming into the estuary. We used this photograph before to illustrate the concept of the internal radius of deformation here. But what I'm using this now is to show you that we had two time series across the James River, and this to illustrate the fortnightly variations of salinity and temperature across the James River. So this is what we have here. First of all, in the upper panel we have this line represents the tidal amplitude. So if it represents the tidal amplitude, what what periods are we looking at here? What does this mean? This is the darker line. So these would be what? These would be analogous to this period and that period, which is different from this period, which is analogous to that period and that period. And if you look at the time scales here, so here we have September 27, here we have October 26, 1 month later. So this would be what? What do you think? Spring tides, large spring tides of the month, spring tides here too, spring tides, large spring, NIP, not so low NIP, NIP and not so low NIP, and again NIP. Okay, so this is just to show us the fortnightly variations of the tide. And the blue line here represents river discharge. So a very large pulse of freshwater input to the James River. Does that mean anything to you, that value of 4,000 cubic meters per second in the James River? And if you remember, I don't know if we've discussed this, but the Chesapeake Bay, the mean river discharge into the Chesapeake Bay is 2,000 cubic meters per year, the annual mean. So you can see here in one pulse, that's greater than the whole mean annual value for the entire Chesapeake Bay, just at the James River. So that's a large value. Just in comparison, an analogous system would be perhaps the Hudson River, which has a mean of, I think, 800 or lower. So to give you an idea, the average for the James River is on the order of 200 cubic meters per second. So that gives you an idea of the strength of that pulse. So that was a tropical storm that went over Virginia and dumped all that fresh water. So that will explain how that affected the fortnightly modulation that I'm trying to illustrate in this figure. So this is temperature, and this is salinity. But as we know, temperature plays a weak role in the density in estuaries. So let's look at the salinity. We'll come back to the temperature if you want. But let's look at the salinity. Just by looking at the values of salinity here, notice that the red line has larger values than the blue line, right? So if the red line has larger values, larger salinity than the blue salinity, which represents the red line, this one or that one? The west or the east point?
East.
The east, that's right. Why is that? Excellent. Because of Coriolis, right? So this would be the east, and this is the west. So you can see clearly here, if we don't look at the influence of the large river discharge, we see that there are periods in which the two lines diverge from each other. Large difference between the two sides of the estuary. This area and, this time and this time. So those times coincide with what time periods relative to the tidal forcing? Neap tides, right? What happened here during these neap tides, we didn't have a large difference because we had the large pulse of fresh water. So imagine, and I'm going to use this same example later on, because this large freshwater pulse flooded the estuary with fresh water, so there was no difference across. It just pushed a lot of fresh water out, didn't allow salinity to intrude. You can see how much the salinity dropped there. So it just pushed the salinity out, and it was uniform all across the estuary because it was a very large pulse of fresh water. So there were the lateral gradients were rather weak. So you have that large difference. You can also see it a little bit in salinity, in temperature here during neap tides, the difference between the two locations. So that also tells us that the lateral gradients may increase during neap tides versus versus spring tide. Okay, so this is the cartoon of the processes that we're talking about. That the mean flow, the estuarine circulation will increase, the yellow line, during neap tides, and the stratification, the water column stratification will increase also relative to spring tides when the estuarine circulation will be hampered, and the stratification, vertical stratification of density or salinity will decrease. Now, can you see that modulation, the fortnightly modulation from the analytical solution that we talked about? Say this, that analytical solution, the density-driven solution that you plotted in your homework. Can you see the fortnightly modulation? Where would you see it? Where would you see the U increasing during neap tides and decreasing during spring tides? How about right there? Maybe. What does that represent? Right, the eddy viscosity is telling us, what does it tell us about the water column? Right, the vertical exchange of momentum, mixing. So during spring tides, what's going to happen to this A sub Z, that eddy viscosity? It's going to increase, so U will decrease. And analogously, during neap tides, this eddy viscosity should decrease, and U will increase. Okay, so again, I want you to keep in mind that these are general concepts that apply to some areas, but not to others, because there are other processes that enter into the problem. Remember that this flow is obtained from what dynamical balance that we assume?
Barotropic pressure and friction. No?
Yes, and what else? Barotropic pressure gradient friction, but you missed. What would drive the water in?
Total pressure.
The density gradient. So the baroclinic pressure gradient. So the total pressure gradient. You qualified it as barotropic, though, but it's a total pressure gradient versus friction, right? But I like your quick answer. All right, so notice here that I've included fortnightly and monthly, and the fortnightly is pretty symmetrical every 15 days, because in areas where consecutive spring tides are similar, then you're going to have a nice fortnightly modulation. But also you're going to have the monthly in the east coast of the U.S., as we had discussed, the N2. The N2 is larger, tends to be larger than the S2. That creates a monthly variations in the tidal modulation, and that causes monthly variations in stratification also. So this is something to keep in mind. In addition to fortnightly and monthly variations, we have seasonal variations that are basically caused by different values of the river discharge. And a way of, well, before we get there, let's think about it a little bit. What do you think the river discharge will do to estuarine circulation? What should it do to it? If you increase freshwater input to the estuarine, what's going to happen to the estuarine circulation?
More stratification.
More stratification, right? Does everybody agree with that? Yeah, that makes sense, right? That's an intuitive response. Right? It's like the intuitive response with the tidal forcing. Well, no, this is more intuitive, and that's the right answer, but not necessarily, because it changes over time. It has a temporal response. The estuary will have a temporal response, and depending on how much fresh water you put in, right? Because if you put a lot of fresh water, what's going to happen to the stratification? You won't allow, the large freshwater outflow won't allow salt to come in. So that will tend to decrease stratification. So it can be illustrated, the response can be illustrated in this cartoon of what happened to the Chesapeake Bay during the passage of a tropical storm back in 1971. So this gave us the foundation to try to understand what happens. Later on, you're going to read a paper that looks at quantitatively how an estuary responds to fresh water input. And you'll see that it also depends on how stratified the estuary is to begin with. But let's assume an estuary that looks something like that. We're looking at it along, so this would be the river, and this would be toward the ocean, and we're looking along the estuary, longitudinal section, and the iso halines would look something like that. So notice that I've colored certain values of the iso haline so that we can see what happens when we have a large freshwater inflow that looks something like this, vertically sheared like that. So if it's strongly vertically sheared, the buoyant water will tend to strain the iso halines more dramatically at the surface than underneath. So you're going to have what's called the surface effect. So that's increased stratification, as you said. But then as the freshwater discharge keeps increasing, you're going to have less of a vertical shear, more of a depth-independent outflow that will push the salt out of the estuary, as you see here. You see, you only see these two iso halines, the blue one and this aqua color. You like that? Or what? What color is that?
Green. It's green.
Okay, green. Right, so that's when the very large river discharge pushes the salt out of the estuary. And then after that fresh water relaxes, retreats, you have this stage which is called the rebound effect. So then you have the salty water rushing back in near the bottom, and these isohalines that were almost vertically uniform strain under the influence of gravity, and then you have an enhanced gravitational circulation, enhanced stratification too, and then it goes back to the conditions that were prevalent before the freshwater pulse. So you have this four-stage response of the estuary. And again, it depends on what system you're talking about and the initial stratification conditions. So this is a basic question that's still unanswered in estuarine physics. How does an estuary respond to freshwater discharge? That's a very simple question, very straightforward question, right? How does an estuary respond to freshwater discharge? But we don't know exactly yet how. Again, you're going to read a paper that talks about, I think it's the state of the art on our understanding on how an estuary responds to freshwater discharge. So the crux is to try to understand how it responds from that expression. So if R increases here, what's going to happen to the estuary, to the estuarine circulation? Just by looking at this solution, if R increases, if you remember, this is a parabolic profile, so that will increase. So what that means is the estuarine circulation will decrease. So you're going to have more outflow but less inflow. But you have to take into account what happens to the horizontal density gradient too. So when you increase R, what's going to happen to G? And that's a big question. If you are able to find a relationship between R and G, you have it made. You'll be famous, and that you won't have to do anything else for the rest of your career. Because we've tried to, people who study estuaries have tried to look at this question or think about these questions for 50 years, or more. So good. For your final project, I expect to see it.
I'll feed you to it.
All right. So here are a few examples on how an estuary responds to the increase of river discharge. And this is illustrated with data. And what we have here is the surface salinity in the entire Chesapeake Bay from close to 50 years of data. So it's a composite of 50 years of data of surface values of salinity. That's the average salinity values for the month of May. So 1 month after the peak in discharge. The peak in discharge occurs in April for the Chesapeake Bay. Why do you think it occurs in April? Why should it occur in April? For those of you who have lived in mid-latitudes, or temperate latitudes, I should say. Yes, the snow starts melting late in March, April, so that's when all the snow in the mountains starts melting, and that produces a large pulse in the river discharge. And that's what's called the spring freshet during April. So the lowest salinities in the Chesapeake Bay are seen in late April and May. 1 month after the peak in discharge. So what you see here is that this is fresh water, and this is salty water. And you can see the salty water intruding and going to the right, and the fresh water going out preferentially here on this side, the left side. And you can guess why that is. Right, Coriolis. So that's May. If I show you, I think the next one is in October, what should it look like? Fresher or saltier? You guessed it. You guessed it right, because you have it right in front of you. No, you don't need to have it right in front of you. Of course, it makes sense, right? After the summer, what happens in the summer in these latitudes? The discharge, the river discharge decreases. There's a lot of rain or precipitation, thunderstorms, but also a lot of evaporation too. It's hot and humid and sticky. So there lots of evaporation. So the net freshwater input is at its lowest at around September at this latitude. So in October, November, that's when you get the maximum salinity. And you can see the dramatic difference. If you compare the lower bay, it's much saltier, right? And if you go up to the upper bay also, you can see the length of of freshwater extrusion toward the south is longer in May than in October. So you can compare the white area, the fresh water coming out. This distance is much longer than in October. So that, you see that effect immediately. Also, if you look at a cross section at the entrance, so you can see the N is here on this coast. You can have N here. We're looking into the estuary, and C is on the right coast. Remember, I've shown this figure before. What three parameters are we looking at on each one of these panels? You have it says right here, the contours, the dark contours are salinity, the white contours are temperature, and the color contours are density, sigma T, density anomaly. Right? So you can see here in July, strong stratification, both, interestingly, both hayland and thermal stratification. The salinity goes from 22 to 31, but the temperature, I don't think I see the values, but I think it goes from 25 to, I think, 18 here. So that's a change in temperature of 7 in the vertical. And that could be important, and this is another aspect that has not been studied that much, the influence of thermal stratification in estuaries. We tend to disregard temperature effects because salinity dominates. But in this case, so like in summer months, you have a large thermal stratification, up to 7 degrees Celsius. So that's, in terms of density, it's around, well, the equivalent to salinity of around 2 salinity units. So that, approximately. So that's something that merits attention, more attention than we have given it. So that's the high stratification. And then during November here, we have, notice that we have barely any stratification, no thermal differences throughout the section, barely any thermal differences. And the vertical stratification of salinity is rather weak. It's restricted to the channels. You only have some weak stratification in the channels. You see that? Only in the channels. Over the shallow areas, it's mixed. So that's the effect of different river discharge. And then now a longitudinal section going from head to mouth, H on the left here and M on the right, M being the mouth and the head. So we're looking at longitudinal sections of surface, of salinity during the spring and during the fall. And you again see the dramatic differences in stratification during the spring as compared to the fall. The salinity is much lower in the spring and also much higher. So in the fall there are the combined effects of cooling atmospheric cooling that tends to cause mixing, but also stronger winds during the fall. So in that example, we see the effects of both of river discharge and of atmospheric forcing. Now here's the same example again that I showed before to illustrate the effects of river discharge that I mentioned it in the previous. Discussion that when we had this pulse of very large freshwater input, there was no lateral gradient in salinity. And again, this is equivalent to the response that we illustrated with a cartoon that shows the depth-independent outflow. So in this case, would be also an outflow that is almost uniform across the estuary, so pushes everything out and causes a very weak lateral or no lateral variations in salinity as compared to the rest of the time. Like you see, there were lateral variations, lateral gradients before the passage of this pulse, no lateral variations, and then significant lateral variations. So that's a large pulse of fresh water influencing the gradients, and in this case, the estuarine circulation should have been hampered during this period when there were no gradients. All right. Now let's look at another example of the combined effects of river discharge and wind forcing, and this is illustrated by the passage of this hurricane, Floyd, in 1999. We were lucky to have had instruments in the water. We had instruments, ADCPs, bottom mounted at those six locations that you see there, 1, 2, 3, 4, 5, and 6. And there are wind measurements right around that area, but on the coast, and another measurement further in the estuary, but I drew it there so that we can see what happens. So what we see in these arrows are the non-tidal flows at different depths. We'll see an animation of this. So we have non-tidal flows at different depths. The red arrows represent near surface flows. The yellow arrows represent somewhere in the middle from 9 to 15 meters depth. And the white arrows are depths greater than 17, 19 meters. So you only see white arrows at these two locations, at this location and at that location, because those are the ones in this channel. You see the channel? The channel goes down to almost 30 meters deep, and this area is around 10 meters deep, all this area. And this instrument was at 7 meters, at a depth of 7 meters, so you only see red and orange values here. So anyway, what you're going to see, look at the arrows. These two arrows represent the wind, what the wind was doing, and you'll see how the flow responds to the wind forcing, which also was combined with a large amount of fresh water input. We had 30 inches of rain during one day with the passage of this hurricane. So you'll see, keep in mind that these are non-tidal flows. We have eliminated the tidal variations, okay? So maybe you won't see the animation. You can see it here. And I'll show it. For our Korean friends, they can look at the website to look at the animation. They're getting upset that we can't. That they can see the animations in the recording, but I can't do anything about it. They've given us a couple of suggestions on how to do it. It's not working. Anyway, you'll see the animation. So notice at the beginning of the animation, that's when the hurricane passes by. At the beginning of the time of the animation. Okay, so get it. Yes, just correct it. Okay, so early on, then you go in there, right around there. There's the. So you see the arrows now. Everything going out. This is soon after the passage of it. The winds are going offshore from the northwest. And you have very strong outflow everywhere across. Right? Okay, so let me show it again. So that's the beginning of the hurricane. When the wind started to be from the northeast. And then right there is the rebound. You see, everything went back into the estuary. So it was a strong outflow and then a rebound inflow. Okay, so let's go back to that a still image of what happened during the peak of the hurricane passage. Okay, so here you have, this is at the peak of the hurricane, and you see the very strong outflow everywhere across the section of the estuary. Keep in mind, again, that these are non-tidal. So how large is the outflow? The strongest outflow is how large? You'd say. The scale is over here. So how large would you say this one is? 1, 2, 3, 70 centimeters per second. So imagine, well, some of you have been at the inlets here. And at the inlets, we have speeds of 1.3 meters per second. But those are tidal. So these are non-tidal. So everything going out at 70 centimeters per second. So we had 24 hours when there was no flood period, no tidal flood into the Chesapeake Bay because of it. All this water was going out. And on the basis of how much water, fresh water came in, we estimated that there was 2/3 of the volume that came out was associated with the river input. It was 30 inches of rain in 24 hours. And 1/3 of that outflow was due to the wind forcing. So when the wind blows very strongly, you have net outflows or net inflows in the Chesapeake Bay. It modifies the estuarine circulation as we saw. But still the tidal flows, you see the tidal flows, water going in and out. But here, when we had so much water coming out because of the fresh water input, then there was no flood tide. There were no flood tides. So the salinity just went down for all that period. No flood tides, no salinity intrusion. And that's why after the hurricane went by, the estuary just recovered and there was big pulse of net inflow into the estuary.
So if the hurricane came through during ebb tide, then those losses would be a lot higher, then, right?
They were. They were
an
indeed.
ebb coming out too.
So imagine that during ebb, the tidal currents were around 1 meter per second. So imagine. So the actual measured velocity during the passage was 1.7. 1.7 meters per second. Okay, any questions?
Is that rebound like due to pressure?
That's right. Set up and set down. Any other question? Okay, so we'll stop right there and remember that. Remember what? Where do I stop recording?